Okay. Are you able to see my screen? Am I sharing well?
Yes, I can see
Okay,
it.
good, good. I think last time we kind of did a bunch of geometry, and today we're going to go through more geometry. I think geometry is actually quite fun and quite like easy actually, I will say. But so we're going to go through a lot of material today, but I don't think any material we touch today will be too difficult to handle. So going to um, assign a lot of homework, but homework you really based on your capability. Just try to pick the difficult one to solve, and I will send both, the homework and the resolution. So you will have a chance to, get with the more difficult ones. And so let's get started. So yesterday, or not yesterday, last time, what we did is that, go through circles. And so um, part of the problems, this part is actually quite, I will think is actually quite fun. And so have you tried this part of the like angle chasing? Um, you know, looks like no one answered. I think, if you haven't tried, I think this is actually a fun part of the work. And so basically, it's actually angle chasing. Basically, circle is a big topic. And so let me just do a few of those problems just as an example. And then let's um, so let me just randomly pick two of those problems. And for example, the second one. And so this is 160. So this is the arc from here to here. You can label it like A, B, C, D. So basically arc AD is 160. And then this part is actually 35. 35 is actually, it's X. It's actually X minus, so basically 35 is actually equal to X minus like arc CD divided by 2. So that's what it is. And then what you see is also 95. So basically this 95 is actually, so 95 is actually twice multiply 95 is equal to AC, is equal to arc AC. So this is the, how everything is laid out. So AC from here is the angle, and then basically X. So it's trying to ask what AB is. So all those angle will add up to like 100 or 360. So we can see that this is 160, and this from A to C. So AD is 360, or AD is 160, and because it's the measurement on the arc itself, and this is on the angle. This is inscribed angle, so it's half of the half of the like angle. And then, so basically from here to here, this is the angle that facing this 95 degree. So it's included all the way from here. So basically it's AC. AC is 95. It's also including D. So basically it's ADC. You will say ADC equals this. And then basically you multiply it, like 95 multiplied by 2 is 190. So minus 160. So basically, if you minus it, it's going to be 30. So that means that this part is 30 degree. So one, it's 95. So it's a inscribed angle. So the arc facing it, facing it, the arc facing it means the arc not including the tip of the angle is double of the angle. So basically you're able to figure out this is 30 degree. So basically, CD is 30. So basically here I can replace in 30. So this is like 70 equal to x minus 30. So x equal to 100. So that's the way that you can figure this out. And yeah, so 100, this is 100. So you figure out this is 100. And then you don't really have to add them together, but anyways, this is just how to solve this type of problem. It's going to be like maybe a little bit challenging, but actually is actually quite fun. So for example, let me choose the last one, supposedly maybe the most difficult one. And so first you will say that it's 80 degree. 80 degree means actually, the angle that going all the way around is actually, 160. So if you label it, this is A, B, C, D, E. And so basically it's actually the arc B, C, D, E. So from all the way here is actually equal to 160. And this one I'm going to use another color to label it. For example, this is the 125. So basically, if I label it, check my labeling all the way to here is actually 250. So basically, it's BA, BD is actually equals 250. And if you add them up, it's actually more than 360. But you see that the only overlapping part is just X. Only overlapping part is X. So basically you add those two numbers, then minus 360, that's going to be the answer for this problem. So this is 410. If you add it, minus 360, that's going to be 50. So X equal to 50. So, so this type of the problem actually, is very fun to solve. And it's also a little bit challenging. And the circle actually has a lot of, tricks inside the circle. One thing is that, if you saw something cross two line, two chord actually intersect with each other inside the circles, so you guarantee to have two similar triangles. This may not be very obvious, but if you really, for example, this one, I connect it, I know that this is also 80 because because this is an 80-degree arc, 80-degree inscribed angle, and it's facing this arc. And the exact same angle here also facing the exact same arc. So basically it's going to be the same. This is 80, this is 80, and this is a vertical angle. So basically you have a similarity. You actually got, two similar triangle. And two similar triangle actually, it actually has a lot of very fun thing. So let's kind of continue on this topic with this chapter 17 on the AOPS. So basically this is actually called power of point. The chapter is called power point. There's a power of point theorem. Power point theorem is actually, talking about line segment, length of line segment on the related to circle and their relationship. Their relationship is very fun. And so the first case is that, two tangent from the same point to a circle are always equal. And this one is actually very, very easy to prove. So AB equals AC. And a tangent point, a tangent line, when it intersect the circle at the tangent point, you actually can draw a radius toward the center, and those radius is actually perpendicular here. So the radius going to be the radius touching the single point at the tangent line is always perpendicular to the tangent line itself. So basically, you actually is able to draw a two congruent triangle like this. And because that's so SAS, the angle is 90 degree. And then basically, actually it's this is 90 degrees. So basically you actually you're using HL congruency, hypotenuse and leg. This is the hypotenuse of the right triangle. This is the leg. So you are able to prove it. Then this part is actually, another. So the product of this is a secant. This is a tangent. So the line segment AB multiply AD is actually the length of the tangent. So this is a very fun. So basically AC is actually the geometric mean of AB and AD. So basically, so there are two ways you actually can, for example, if you are asked to draw a geometric mean using the constructive method to draw a geometric mean, you actually can use this method, basically. You can draw one line set two. So this is a quantity A, another quantity B. So you can draw line A and then line B, and then basically, if you draw a circle here, if you draw a circle here, and then its tangent line is actually geometric mean of those two lines. And why? Because you are able to draw this, you add those two lines here, one line here, one line here. Because this is a tangent line, so this angle basically is 1/2 the size of this arc. 1/2 the size of arc. So this angle, and this angle is the inscribed angle of the circle, it's also 1/2 the size of this arc. This topic we have been, discussed last time, through our notes. So basically, let's see that. Um, yeah, so basically, a tangent line and another, this is a tangent line and a chord. So basically, this is theta. Theta is the whole arc. Basically, the angle formed by the tangent and a chord basically is the um, half of the arc the angle is facing. So basically, this arc is twice the size of the angle it's facing, and this arc is twice size of this arc it's facing. So this is just, and add together, the whole circle is 360 degree, and this is actually a straight line. This is 180 degrees. So basically, the whole thing will add up this way. So basically, the power point here is that this is the angle, and this is the chord. This is the tangent, and the chord it's facing. It's just 1/2 of the arc size. This is also 1/2 of its arc size, and this is a shared angle. So basically, by a similarity, they actually is similar. So basically, triangle ABC is actually similar to triangle ACD. So because they are similar, so basically, this is obviously the longest one. So basically, this is the longest line on the triangle, and this is the second longest line on the triangle. So basically, the ratio between the second longest and the longest, so I will say second longest and the longest. This is the ratio. This is the two things. So basically, AB over AC is actually equal to, so initially I'm using this little triangles and using the bigger triangle, ACD. For ACD, the second longest line is AC over AD. So basically, if you cross multiply, AC square equal to AB multiply AD. So this is, part of the point theorem. And then this is even more interesting part is that if you have two line that, two sequence intersect outside of this circle, then AB multiply AC equals AD multiply AE. It's actually very easy to prove. Basically, you can add a tangent line here. So, their product, both of their product actually will be the same as the square of their single tangent. So basically, all those products will be the same. And this one actually, BA multiply AC. So BA multiply AC. So it's always on the same line. The product is actually, the segment on the same chord. And so those cross product actually will be the same. So why they are the same? You possibly will ask for this question because this is a different shape than this. It's actually extremely easy to prove. Basically, you just have to remember that any intersection, any intersection line inside a circle will for sure create like, two pair of the similar triangle. So basically, I will say that um, this is BAE. BAE. And so basically you see that those two angle will be the same because they're facing the same arc, EC. So basically, when I was doing the similar triangle, I need to get my sequence right. So A is this triangle. So I will use double arc here. I use a single arc here. These are vertical angle. So A, so so just one arc, two arcs angle, ABE. You can write it ABE is actually similar to triangle ADC. ADC. So basically those actually are similar. And so because those are similar, and then BA and the AC, BA and the AC, BA and the, so basically you actually can divide this. So BA multiply AC. So basically what I can do is divide AC on both sides and divide the AC on both sides. So this going to be canceled. BA, then I'm going to divide AE on both sides. AE on both sides. So AE got canceled and AE. So basically BA over AE, BA over AE, AE is actually, BA is the angle faced by no mark. So basically, and AE is the side faced by two arc. So basically is equal to DA. DA is the side faced by the angle with no mark. So basically, and the AC is double arc. So basically, what I'm trying to prove is that just, angle with no mark, angle to arc tech. So basically, because the similarity I can tell. It looks very confusing, but if you mark it right, you definitely will get this right. So basically, it's just in geometry, circle and the similarity actually has a lot of things that you have to, you know, um, hidden in the picture. You have to spot it and find it out. They also has a lot of product relationship. So, yeah, they are like proof of this. And I think I just go through that. So we'll just assign as homework. It's not very difficult. As soon as you're getting used to it, you have to, because with circle, because there's a 1/2 relationship with the length or with the angle of the arc for inscribed angles. So basically you actually will not just log the angle by itself. You also look at the angle by it's the arc it's facing, and then trying to start from that arc, locate all the other possible angles that are already drawn. So you will be able to spot all those, saying angles, and you from there you are able to spot more like similarity. So uh, yeah, so there's this one. This one, let me redraw it. So basically, it's so the opposite triangle. So this is a pair. Then this is another pair of similar triangle. So if you draw it this way, this is also similar because this angle, those two angles are the same angle arc BE is facing, and they also has a vertical angle. Then you don't even really need to use the vertical angle because, for example, this angle is both facing this arc. Then if I change the color, and this angle is actually both angle facing arc CD. So basically, just using the arcs they are facing, you're able to prove that they exist. Like, so inside the circle, the similarity, um, you need to like getting used to it as if it is parallel, because in a parallel line because it's quite intuitive, because you know that this is corresponding angles, these are alternate internal angle, alternate exterior angle. So, but inside circle, it's not very obvious, but you just remember this fact that, just as if like a vertical angle has two pair of equal angles, and a crossing inside a circle actually create not just two pair of the vertical angle, it's actually create two pair of similar triangle. So that actually gave you more power in terms of doing work. And then it's just the fact of you have two pair of similar triangle, then these products, these fancy product are just byproduct of the similarity. And that's all. And so that's that. Yeah, I think that's about how much we are going to touch on the circle and lines and triangles and the similarities. And we will go through those very quickly. And then like these are the triangle classification. I'm not going to go through it, it's just too simple. And the part of the triangle is a lot of problem going to be, touched on, like the medians. And the median of the triangle, the special part of the triangle, just remember that the median basically is you connecting the vertex toward the opposite side middle point. And then they will all coincide at a point. The coinciding point is called centroid. And the centroid basically is gravity center. And also one thing nice about this is actually it's dividing this triangle into equal area 6 pieces. So all those pieces looks like different, but the area of those 6 pieces are exactly the same. So like, if you, so there are problems in the contest asking you to cut, a cake equally with odd shape. And then centroid, the media is actually used quite often to achieve this type of the, feat. So it's actually very easy to prove that, all the area. Let me try to just prove all the area is the same. And it's actually using a feature called, height and base. base height product. So the area is of triangles, you know, the area of a triangle is 1/2 base height. So basically, you can argue that, this part, the yellow part, and this is the blue part, is actually have the same area, even they look different because they have the same height. They actually share the same height. They just use different base, but since it's the middle point, their base actually is the same. So basically this area is the same. Then basically, you can use the intersection point. You can use the intersection point at here, centroid. Then those little triangle has the same. So those little triangle, this little triangle has the same area. So those two are the same. So you can also prove those two are the same. So basically the little triangle sharing the side and sharing the centroid have the same area between them. Then because the bigger triangle and the minus the lower triangle actually is the same. So basically, we actually prove that those two triangle also has the same area. Those two have the same area, and they also divide into same area. So basically, all four of those has the same area, and so basically, all four have the same area. We actually prove that adjacent triangle has the same area. So we prove that triangle on the same side has the same area. Also, triangle that adjacent to each other on the same corner also has the same area. So basically, it's all same area. So basically, this median thing has a lot of interesting things to think about. It also has 2-to-1 ratio. So basically, this length BG over GE, BG over GE, AG over GD, and CG over FG. Those are all have the same ratio of 2-to-1. So that's a very important fact. And then we have the angle bisector. Angle bisector is actually a very important concept. And so angle bisector actually will intersect at each other. So basically this angle is the same, this angle is the same, this angle the same. So they actually will intersect each other at the point called incenter. From the incenter, you actually can draw an incircle. This incircle actually tangent to the all three sides. So the incenter has a radius called R. So basically, actually, there's a formula for this alternative area formula for the triangle. So the triangle's first formula is that the area of a triangle is actually equal to 1/2 of the base and the height. It actually is also equal to 1/2 of the radius of the incenter or incircle, then multiply the parameter. Parameter means that, it's actually quite simple to see it this way. You can divide this circle into 3 triangle. And then each triangle is the side multiply the incenter's radius. So basically, this triangle is at BC multiply 1/2 R. And so if you add the area of those 3 dividing triangle, you actually get, the area of triangle is 1/2 radius multiply perimeter. Sometimes they also say equal to radius multiply semi-parameter. So this is S. S is just semi-parameter. It's S usually is equal to 1/2 A plus B plus C. And so triangle also has another area formula. So this is the second set. The third triangle area formula is actually, it's a Heron formula, and the triangle's area, the area of a triangle is actually equal to S. S is the half of the parameter multiply S minus A multiply S minus B multiply S minus C and the square root. So this is the third formula. And so, and then we have the perpendicular bisector. And the perpendicular bisector will create a, this is called a circumcircle. This is in circle. So basically, around the triangle, we have 2 circles. One is in circle, one is circumcircle. And then we also have altitude. Altitude has also center. And the triangles, like the triangle congruency, actually, I think every one of you already learned that, because that's the early part of geometry. So I'm not going to go through it, but I'm going to go through some similarity, because similarity is actually a little bit more confusing and a little bit more difficult in terms of solving the problem. So one of the problem is that angle bisector theorem. Angle bisector theorem is actually going to create a bunch of the angle bisector theorem states that if you have a triangle ABC, and if you have a AX is bisecting the vertex of A, then you actually have AC over AX is equal to AB over BX. Also, you can write it a different way. It's also actually, if it's angle bisector AC over AB is also equal to CX over BX. So basically the side ratio is equal to the opposite division ratio, and also the side over the opposite division equal to this side over this division. So how does it work? Let me try to prove it. And this is actually extremely easy to prove. And all you need to do is extend this bisector and also draw a parallel line toward AC through B. So if you do that, basically, because it's a parallel line, then this angle will be equal to this angle. This is alternate interior angle, AIA. Then basically this angle is actually equal to this angle because this originally they are saying, and these, so this AB, let's say D, A, B, C, D, X. So angle DAB and the angle BDA are the same because the angle, this is just, you know, through AIA, it transforms this angle over here. And so this is angle bisector, they already saying. So this has to be the same. If they are the same, then the side AB and the side BD are the same. So this is the same length. Same length, and basically, you know, I have I basically, you know, using the triangle similarity. So ACX is actually similar to ACX is DBX. So those two are actually similar. Because they are similar, so I have AC. AC is the parallel. So basically, you know, if I have to write ratio, so the other side is actually BD because those are parallel lines. They are corresponding to each other. AC over CX. CX basically on the corresponding side is here is CX and the BX. So those are the same. And then basically BD could be replaced by AB because those are the same with the isosceles triangle. So basically BD, I replace BD with AB and the BX. Then basically I actually get this proof. So it's a very, very simple to prove theorem, but it's quite useful. So basically, the angle bisector actually, you know, is hiding some ratio. Those ratio are not very obvious because those this triangle ACX and ABX are not similar. They are not similar, but they still have the ratio. Why is that the case? Because if you draw a bigger picture, you can create a related similar triangle to one of the triangle. Then this similar triangle actually related to the original side with a isosceles triangle. So that's why, you know, it can be all linked together. So this part is actually, you know, quite important. And so similar triangle, actually, you know, let me just do a few more of those problems that similar triangle, you actually have to look for it, expect it, and then also trying to really hunt for it. So let's trying to do a few, just getting used to it. And this is like AI. So AX and BY both are bisector with which intersect at I. Then we need to prove AI over IX is actually equal AC over CX. I'm going to prove it in several different ways, so you will just getting used to it. First, you know, if it is angle bisector, it's going to intersect at the center called in center. So the in center is actually also the intersection of the third angle bisector. So I can create an extra line like this. This is the extra angle bisector which bisect AC, bisect angle C. So if the C is the angle bisector, then I actually have, just looking at this smaller triangle, ACX with this extra line as the intersection or as the angle bisector, it actually, you can apply the angle bisect theorem directly. So AI over IX, AI over IX equal to AC over CX. So basically, angle bisector theorem could be written in two ways. So one way is that, the side over the opposite cut is equal to the other side over the opposite cut. Another way is that, the ratio between the side is actually the corresponding ratio between the opposite cut. So basically here, after I add an extra line, AI to IX, for this triangle, it is the opposite cut. The ratio of the opposite cut is equal to the ratio of the side. So I prove it directly by just adding a line. And yeah, so basically, without this line, you still can prove it. Let me show that, usually when you're doing with the geometry problem with similarity and other things, usually there are a lot of ways that you have a lot of different solution. And so basically here, like AI over IX is actually equal to just looking this way as this angle. ABX, AI over IX is actually equal to AB over AX. So basically AX. So basically this is the AI over IX, AB over AX, and AC over CX. And so just looking this angle differently. So here, this is another angle bisector. The angle bisector is AC over CX. For this big triangle, ACB, and with this angle bisector, this is the side over the opposite cut equal to this side over this opposite cut. So basically, if you're looking on this angle, basically you will find that, AC over CX is actually equal to AB over BX. So basically, AI over IX equal AB over, so this actually, those are equal. So use this equation, I actually will link them together. So this type of problem, basically, you may have different ways to solve it, and actually, looking at different angle, because angle bisector theorem definitely is a tricky one to apply, because it's not very intuitive, and you have to looking for it. And usually you have to write down, and with this, for example, with this angle bisector, what's the relation I can have? You can write it in either two way, side over the opposite cut, or cut over cut, then side over side. So basically you can lock in two different ways. And um, so like this is the theorem is actually used quite often to find side ratio. You actually, for example, let's also trying to show this one. This one is also a fun one. And so this actually is the illustration for the geometric actually harmonic mean. So let's try to do this problem first. This is another way to do the geometric mean. So we have been able to construct geometric mean with circle. Like for example, if you are able to like draw one line and then draw the second line overlapping it, just extend it longer one is here. So if you draw a you can draw, you don't have to use this as a diameter. You can just draw any circle passing through it, basically. And then actually the tangent line going to be the geometric mean of this and this. So basically, this line, let's say A, B, C, D. So AD square equal to AB multiply AC. Another way to construct a geometric mean is actually using the right triangle. Let me show how. So for example, this is the divide a hypotenuse into 4 and 8. So I have a altitude divide altitude of a right triangle, divide this opposite side into 4 and 8. Then what is the length of the altitude? So altitude, what's the length? So there are certain places you, especially in the computation, you're always looking for similarity and always looking for the, angle, same angle. And in the right triangle, when you draw altitude from the right angle side to the opposite side, you immediately have three similar like triangle. So this is the first little one, the medium one, and the bigger one. It's really easy to prove because, use angle similarity. The bigger one and the medium one share the same angle. They are also both right. So by angle, those are similar. You can also prove the smaller one with the big one using the same methods. And because both smaller and the medium one are similar to the bigger one, so they are similar to each other. Because the similarity also has the, transmissive property. And then because those are similar, so basically this is the short leg over the long leg. So for the smaller triangle, short leg over the long leg, and equal to for the median triangles, short leg over the long leg. So for example, for x, I can use h equal to h over 8. So h squared equal to 32 and h equal to actually, that's 4 square root of 2. So basically, this is 4 square root of 2. But it's actually a very simple way to construct a geometric mean. For example, if you have two line segments, so one way is to draw tangent, another way is draw right triangle. For example, if you draw those two lines, then if you draw a half circle, then draw a height where you hit the half circle, it's going to be the right triangle. That's the height is the geometric mean of the geometric mean of those two line segments. So that's the fun part of the, and so let's trying to see the, this is the harmonic mean. Harmonic mean actually, to how construct harmonic mean with this picture. This picture is extremely easy to prove. And so these are the parallel lines. Those three lines are all parallel. And the X and Y on the end, then you kind of draw a connection at the bottom, then draw a cross line and intersect at C and D. And then actually, so the fun part is that 1 over Z is actually equal to 1 over X plus 1 over Y. And why? Because it's actually quite easy to prove. So because this triangle, this little triangle and this bigger triangle are similar. So basically, Z over X is actually equal to DF over BF. And so with this group of similar triangle, then with this group of triangle BCD and BEF, you have Z over Y. So we have Z over Y equals BD over BF. Then you can try to add them together. So basically Z over X plus Z over Y equal to BF and DF plus BD. So DF plus BD basically is equal to BF over BF equal to 1. So then I'm going to divide Z on both sides. I will get this. So Z basically, like harmonic mean of two number basically is actually like is actually 2 over 1 over X plus, so basically, Z with this, we can tell that z is actually equal to 1 over plus 1 over y. If you multiply 2 on both sides, basically this is the formula. And so basically, you know, z so 2z is actually equal to 2 over this. So the fun part is that you can actually draw the line over here, and if you try to extend it longer, and so this line is actually going to be double this line segment. If you draw another line here and draw this D, C, D, E, F, G, let's say G. So BD, so DG is actually equal to the, DG is double Z. So it's actually the, it's actually is the harmonic mean of, you know, those two values. So, you know, like together with arithmetic mean, geometric mean, and harmonic mean, those are the three Pythagorean means that, you know, like people already master like 2000 years ago. It's just show, you know, how advanced the math was when it's even in the classic Greek time. And people already understand a lot of geometry and a lot of fun facts that link the those methods together. So let's go to the quadrilaterals. So the triangle. So we have been covering the circle. The circle has a very fun fact, and so it's the arc one, you know, inscribed angle 1/2 relationship, and also the, like, you know, power of point theorem. So basically you are able to construct, you know, a power relationship, you know, geometric mean using the line segment. And we are able to, you know, multiply those together to be a constant. It's actually the length of tangents power, then, you know, cross line, you can multiply each other. And it's a very fun thing. And then with the triangle similarity, with the triangle similarity, we actually, you know, find more fun things, like the right triangle. With the right triangle, you have generate three of those, and you can find another geometric mean with this method, with the construction. And we have the, you know, angle bisect theorem. And we also look at one example is actually, you know, with two angle bisector, you actually can use the ratio in different orientation and look at in different ways to link them together. And they are common setup for the and similarity. So triangle similarities, there are a lot of setup you have to remember. So those are come very often is that, so let's just borrow this picture. Yeah, let's just borrow this picture. And so the parallel line definitely generate a lot of similar triangle. And so, for example, ACB and FCE are similar. Then also this is in the opposite direction. They have shared angle direction. For example, CD and BEF actually are similar. So is, FCD and FAB are similar. So basically, those are the two common setup. One setup is this way, the other setup is this way. So, and then another setup is the right triangle. Basically, if you have right triangle, and this setup will create three similar. Then you have, circle intersection. Basically, that will create two pair of the similar triangle within the circle. So these things that you kind of just, know where to look for, and then go after it. You will usually find very good result. And so let's go to the quadrilateral, and also there are several fun facts on the quadrilaterals. And quadrilaterals basically is just have 4 vertex versus triangle has 3. And the total angle size is 360 degree. And the quadrilateral is also diagonal if the diagonals are perpendicular. And for all the also diagonal, like quadrilateral, actually it's very easy to calculate the area. So basically actually 1/2 of diagonal 1 multiplied diagonal 2. So basically that's, and a lot of also diagonal is actually rhombus is one, also kite is another one. And then you don't have to be either kite, or you can have something that, it's also diagonal, it's not rhombus nor kite. You still can use this formula. It's just, it's just look at, for example, if those are also diagonal, you can draw like a bigger, if you can draw a bigger rectangle. So basically for each quadrant, the area within the quadrilateral and outside of quadrilateral are exactly the same. So you are able to use 1/2 diagonal 1 multiplied diagonal 2 to really calculate the area. And the other part is just another area you actually looking extensively for the similar triangle is the trapezoid. Especially, first, let's say it's a generic trapezoid. It's a generic trapezoid. You actually, if you extend the top to the tip, you actually find this and this similar. And then if you do cross diagonal, you actually find this and this similar. So with similarity, you actually is able to, with using the ratio, and is able to calculate the trapezoid, like area size between all those. So that's actually a quite important thing. Also, with trapezoid, especially especially if the trapezoid is a isosceles trapezoid, then basically, if I draw isosceles trapezoid, then those two triangles not only are similar, they're actually congruent. Then basically, you are able to calculate areas that way. And even with not congruent triangle, basically area of those opposite triangle actually is the same. So the area is the same. And but so those are the area is the same. You can use the height. Use you height area. You know, for the area of this triangle and this triangle is the same. Let me using this example. So the area of this triangle and this triangle is the same. Then the area of those two triangles, those are on the opposite side, is the bigger triangle minus the common triangle. So basically those are the area are the same. So when you're doing the the trapezoid problem, you always has to be aware of those facts and then go along with it. And um, the middle, if you connect like the middle point of the legs, it's called median, and it's also called mid segment. Basically, the mid segment for the mid segment and median for the trapezoid, it's actually the same thing. But the median and the mid segment for triangles, those are not the same. So for the mid segment of a triangle, it actually is this, and the median of a triangle is actually this. So basically, those are different. But median and mid segment for trapezoids, they are the same thing. And the area of the trapezoid is the median multiply the height. And so that's the trapezoid and parallelogram. And the parallelogram and within the parallelogram, it actually has a lot of fun fact that you can prove with the triangle like congruency. And so let me just prove one of those for you. So basically so by definition, the a parallelogram have two opposite sides parallel. So right now, what we are trying to prove is that the opposite side actually is equal length. So basically, how do we do that? It's actually not very difficult. What we do is that we draw a diagonal. Then basically, because those are parallels, if this is parallel, then basically this is alternate interior. That is the same. Then if we looking at this direction, those are parallel with the same diagonal, and this is the same. So basically, with those two triangle 1, triangle 2, basically with angle side angle, because this is the shared side, and they have also two angle the same. So those two triangle are congruent. It's congruent, so basically their side is the opposite side is actually equal. So this is actually, to learn math and understand math well, I think especially, those theorem and the fact, and if you are able to prove it and at least understand what they are, the reason behind it, it's going to be very helpful for your long-term development. Not just remember the fact, but just understand how the fact are derived from the definition. That's going to be very important. And the rhombus also has a lot of fact. Basically, you can also do it exactly the same way. And has a lot of congruency thing. And so quadrilateral has some very important things that, it's not so obvious, but could be very advantage for you. So let me just show this fact. It's very fun. So you have Pythagorean theorem. So Pythagorean theorem states that a square plus b square equal to c square. That's for the right triangle. And we have a similar like Pythagorean theorem in the parallelogram. And how does that works? And it's for any parallelogram. So basically, that's going to be a very, very fun thing. Let me show what is the fact. Let me also show how to prove it. So basically, the sum of the square of the side of a parallelogram equal the sum of the square of its diagonal. So basically, if you have a parallelogram like this way, and for example, if this is the side A, this is side B, this is also side A, this is also side B, then we have a diagonal one, D1 and the D2. So basically, this fact, this kind of Pythagorean theorem states that, a square plus b square plus b square equals d1 square plus d2 square. Or you can write it this way, 2a square plus 2b square is actually d1 square plus d2 square. So isn't that fun? And so let's try to prove it. So part of the, so I kind of just a math lover and, just starting from very young age and just love math and like the beauty of it. So if you're really into math, there are a lot of fun things behind it. And there are a lot of interesting story and also very practical. It's just kind of, give you a lot of power in terms of getting to a higher degree and getting good school and all those things. So basically, it comes with a lot of bonus on this. And but one thing that hard about math is that a lot of fact you cannot grasp or understand right away. So the best thing to learn math is actually it's not like a short-term spike. It's not like you have interest in 1 day and it's done with it for the next 30 days, just 1 month do hard. So the best way to learn math is that each day you spend about 1 to 2 hour quality time, very quiet, just everything, you forget about anything that you don't do social media, you don't do YouTube, but just focus on the math and solve some really interesting problem and trying to challenge yourself on more difficult problems. And that's the way to sharpen. And also trying to touch the difficult concept. And a lot of difficult concept, actually, you have to learn it through time and repeatedly touching it, repeatedly exposed to it, repeatedly practice it, then you will become very good. So that's the way that to learn math. And so this is one of the things that, keep fun. And so if we draw a parallel line, and if we double the size of it, just extending it, then basically this diagonal 2 is actually translated over here. So translated from this position to this position. And then basically we can draw a height here. So basically we will say that this is A, this is B, A is here. So basically this is A. This is still A. I write it the wrong way. This is A. This is B actually. So this is B, and this is also another B. And then I will say this is C. I can label it as a C. And so this is D1 and D2. D1 is the longer diagonal and the D2 is the shorter diagonal. So the D1 square is actually equal to B plus C. So the height dropped to here. So this is the B plus C is the here. B plus C square plus, then basically I have this the height. I don't know what the height is, but I have A and the C is a right triangle. So the height square, so plus height square is actually A square minus C square. So basically plus A square minus C square. That's D1. And then D2 square is actually equal to, this is B. I translated over here. So this is another, so it's actually B minus C. It's actually B minus C square plus also the height. The height here is A square minus C square. So this is D2 square. So if you add them together, so D1 square add D2 square, actually B square on the top, as I'm trying to expand it, it's going to be plus 2BC plus C square plus A square minus C square, and then plus B square minus 2BC square, 2BC plus C square, and plus A square minus C square. So here, basically, so in each line, C square got canceled out. And across those two lines, I got 2BC got canceled out. It's actually equal to B square, 2B square plus 2A square. So this is actually an interesting fact. So basically, this fact is almost like a Pythagorean theorem for parallelogram. So it is the side, the square of the side, A square plus B square, but it's all sides. So basically you have to double it. It's actually equal to diagonal square. Diagonal because you don't have just one, you have two. So basically it's actually, D1 square plus D2 square. So that is one of the fun fact. And it's also practical fact. So basically let's try to apply this fact to calculate on something. So use previous exercise to find the length of the median. So you actually is able to find the length of the median if you measure. So for example, this is like A, B is 5, and AC equals 7, BC equal to 6. And the median basically is the connect to the middle point. So trying to find the length of the median, how do I do that? That looks really daunting, but it's actually not very daunting. You actually can expand this triangle into a parallelogram by just doubling it. So basically, if you're doubling it, 5 and 7 became the side of the parallelogram. And this 6 is diagonal 1. And I'm trying to find the median is just 1/2 of diagonal 2. So basically, let's try to calculate it. So the square of all the side is actually, 5 square plus 7 square and double it, that's 2, is equal to 2, equal to, let's say that diagonal 1 is 6 square, plus and median. Median actually just 1/2 of the diagonal. So I have to, let's say median as x. So basically I have to say 2x square. So basically, we can say that is 36 plus 4x square. This is 2. And this is 25 plus 49. And it's 74. So 74. And then we can factor out a 4 on both sides. So basically these two got canceled out. Factor 4, we got 37. And so basically if we divide by 4, basically I'm dividing 4 on both sides. And divide by 4 on this side, this is going to be 9 plus x squared. And so here I minus 9 on both sides. Going to be 28 equals x squared. And this is like 4 square root of 7 equals x. So basically, you are able to find, so we are able to find like, a certain line. So basically, knowing this Pythagorean theorem almost in the parallelogram give us capability to find the length of the median of a triangle given 3 sides, given the length of 3 sides. So that's a fun thing to know. Okay. So then let's go to the polygon. And the polygon, I think we already touched that before. We prefer using exterior angle instead of interior angle because that's always a 360. And then I think for the polygon, I think we'll only touch the like 2 type of the polygons that could be extensively tested in the contest. One type is the hexagon. The other type is the not pentagon. The other type is the octagon. So first, let's learn some terminology. Is that for all the polygon, all the irregular polygon, we actually is able to draw 2 circles that relate to this polygon. For example, this is a hexagon. And I can draw 2 circles. One is circumcircle, which link together all the vertex. And in the last class, we also showed that, if given whenever you do the regular gun, it always has some advantage to add a circumcircle because all the triangles related to this polygon became inscribed angles. And you can use arc to find the angle instead of just using the triangle. It gave you a huge advantage by doing that. But then we also will learn the terminology on the angle, regular angle. And we also can draw a inscribed circle. Inscribed circle is just tangent to each side at the middle point of each side. And there's a terminology for all those. So each side is just, the side length, you would say. And then the measure of OA, they call it the radius for the circumcircle, for the regular gun. And then between the distance from the center to the middle point of each side is called apocen. Apocen, I think it's called apocen. So basically, yeah, I think I try to play so it is called apocen. And so basically, if we do the triangle, and it's actually is very advantage. You actually is able to use the trigonometry function to find the like the relationship between them. So tangent theta is equal to 1/2 of the side length over the apocen, and the sine theta equal to 1/2 length of the side over the circumradius. And let me, to the last point, let me cover the, the definition of the trigonometry functions. And because even it's not formally tested at AMC10, it's definitely going to be tested at AMC12. And it's also a good concept to master because it's used in a lot of formulas in the area calculation. And so I'm going to touch the concept of the trigonometry, and let's go through that very quickly. And so the trigonometry, first we're going to touch the definition of the trigonometry function. Then we're also going to go through the how to remember the trigonometry definition, and also how to remember the trigonometry function identity. So there's identity of the trigonometry function. This is what I'm going to cover today. And so to remember the definition of trigonometry function, we're going to remember a funny spelling word called SOHCAHTOA. And let me try to spell it out for you. And so basically, you will say that SOHCAHTOA. So it's a 9-letter word. And so, ka means sound like coughing, and toa. So it's actually related to, so we are not going to label the trigonometry, the side of the functions this way. We're going to change the orientation. So A is still going to be here. C is still going to be right angle. B is going to be here. So here is just the A, and opposite A, that's BC. I'm not going to label as A. I label it as O. That's because that's opposite. And the other side, going to say adjacent. I'm going to use the adjacent. and this side going to be called hypotenuse. So basically, I'm going to use this to define it. So S means so sine. So the sine A is actually equal to, in this triangle, if you label opposite, adjacent, and the hypotenuse is actually equal to opposite over hypotenuse. So opposite over hypotenuse. And the cosine A going to be equal to so cosine equal to adjacent over hypotenuse. So basically it's the adjacent over hypotenuse, and TOA is the tangent. Tangent A equal to opposite over adjacent. Opposite over adjacent. So with so-called TOA, you're able to remember 3 of the 6 trigonometry function. The rest you can just you can just know the reciprocal of them. So what's the reciprocal of tangent? It's cotangent. So cotangent A is actually the reciprocal of tangent. So that's going to be adjacent over opposite. Then the sine, the opposite of sine is always cotangent or cosecant. So basically, the sine and cosine, only tangent has the cotangent as opposite. For sine cosine, its opposite is, it's cosecant. CSC A equal to hypotenuse of over opposite, and then the cosine is opposite is secant, SEC, secant. And secant A, basically opposite is going to be H over A. So this is how you remember the definition. And trigonometry function, don't be daunted by the trigonometry function. It's just a shortcut for the ratio between it's a shortcut for the ratio of the side of a right triangle. That's all it is. And then basically there are 3 trigonometry function identity, this one and this one and this one. And you have to be able to draw the triangle, draw 3 triangle around the unit circle. Let me use the unit circle, and the picture is in the Wikipedia. It's extremely helpful. It's a trigonometry function. So basically, yeah. I think they changed layout. I don't see the picture anymore. I think I should have saved the picture anyway. Let me just draw it. But they actually has a better drawing. this is the unit circle. It's all about unit circle. Let me just draw it myself. It's not very hard to draw. In fact, you actually have to draw it. So basically, this is just my trick I'm going to share with you. And just dealing with the trigonometry function, a lot of time, especially going through the test, if you are not given a reference, and the first thing you actually is to write out the important formula first before you even do anything. And this picture is extremely important. So let me just copy the pictures and extend above this picture. And so yeah, so basically a unit circle is the circle with a radius 1, and the sign in the unit circle, basically, if the inner circle is the 1, then one side is the sine, the other side the cosine theta. And it's actually, it's actually quite simple to understand, because if you have any, like, if you say this is hypotenuse, this is opposite, this is adjacent, if you divide, the sine is just equal to opposite over hypotenuse, and the cosine is just, equal to adjacent over hypotenuse. So basically, imagine that if I standardize the hypotenuse to be 1, if I shrink this thing to a unit 1 circle, basically, because that's hypotenuse is 1, so basically the sine just equal to opposite, exactly equal to opposite, and cosine is exactly equal to adjacent. So that's really obvious. So above the obvious thing, usually I always draw 3 circle, or just 1 circle, or 3/4 circle. I don't have to draw the full circle. And so you can draw something like this. And so this is 1. And so this is sine. So this part is sine. This part is cosine. Then if you draw this is a tangent. Then this is 1, because this part, x, is 1, 0. And this is actually tangent x. So this line, geometric meaning. And this is tangent. This is 1. This is the radius 1. And this side, this the hypotenuse. In the smaller triangle, in the smallest triangle, the hypotenuse is 1. Right now, the x is 1. And the hypotenuse became secant. And then I can draw an even bigger triangle here this way. So basically, I can drop down here. And this, because it's this side, the height is 1. This is a rectangle. This is a rectangle. So this 1 got translated here. So the y side is 1. And this here is actually the top side is cosecant, and this side is cotangent. So basically, I'm going to write out all those 3 triangles. So if you write it this way, the inner one is 1 cosine and sine. The middle one is actually, this is the one. This side, the lower side, going to be 1, and this side is tangent. And this is the secant. And then outside the bigger one. So the biggest one is actually this side going to be 1. So a triangle, you can assign one of the side to be 1. So we take rotation from hypotenuse to be the x orientation 1, the y orientation 1. So this side is going to be cotangent, and this side cosecant. So with those are all 3 right triangle. What's the importance of those? If you are able to draw this, then it's possible to write down the trigonometry identity very easily. So here is the cosine square A plus cosine A, or sine sine A square equal to 1. So this is the first identity. The second identity is actually, the tangent. So this side as this side equal to this side with the Pythagorean theorem, and tangent A square plus 1 equal to secant A square. And then this one is that the cotangent A square plus 1 equal to cosecant A square. So basically, I'm going to find that picture because that picture is very nice. And I just, it's kind of, for whatever reason, it wasn't there anymore. I'm going to find there's a nice version of the showing. So basically, just introduction to the trigonometry, and if you are able to remember the definition and remember the drawing, the unit circle drawing, and those are 3 triangle that scale from the inner to middle to the out, and on 3 different, sine function, a trigonometry function identity. You are able to write it out, and then there are a lot of things that, after you able to draw this, it's going to be very easy, very natural to really write them out. So yeah, we have another geometry class. Next class, we are going to touch those and going to touch more on the analytic geometry, and going to touch on the 3D geometry. But anyway, I think we have enough for today, and have a nice one.